October 4th, 1957. A room full of Soviet engineers in Kazakhstan is completely silent. They are listening to a sound no human being has ever heard before. It is coming from above them. From somewhere between the Earth and the stars, a place where, until this moment, nothing made by human hands had ever been. The sound is a repeating pulse, a clean, steady tone. A junior radio officer named Lieutenant Borisov is the first person to confirm the signal. Then the signal drops below the horizon. 90 minutes later, the signal returns, right on schedule. And then they understand what they've done. The satellite was called PS-1, which stood for Prostейший Sputnik, the simplest satellite. That name was chosen deliberately because the version they had originally planned, a sophisticated, instrument-laden spacecraft weighing over 1,000 kilograms, was running behind schedule. So they stripped everything down. They kept a radio transmitter, 3 batteries, a pressure sensor, and a temperature regulation fan, and they sealed it all inside a polished metal sphere just 58 centimeters across. This was not what anyone had envisioned as the first object humanity would place into orbit, but it was what they could build in time. And time, by the autumn of 1957, was the only thing that mattered. To understand why, you need to understand the world these engineers were living in. The Second World War had ended just 12 years earlier. Nazi Germany had been on the verge of developing the world's first intercontinental ballistic missile before the war ended, and in its aftermath, both the United States and the Soviet Union had absorbed the remnants of that program, the technology, the research, and in many cases, the scientists themselves. There is one man more responsible than any other for what happened on that October night. His name was Sergei Korolev. He held the title of Chief Designer. By 1954, he was lobbying the Soviet government to build an orbital satellite. And he had a partner in that fight, an engineer named Mikhail Tikhonravov, who had been quietly writing technical papers on the possibility of spaceflight since the late 1940s. The two had met years earlier as young men in an amateur rocketry group. Now, decades later, they were about to change the world together. Here is the thing that almost nobody talks about when they tell this story. Sputnik very nearly didn't launch at all. The original plan was to launch a satellite called Object D, a complex, scientifically equipped spacecraft. By late 1956, it was clear that Object D couldn't be ready in time. The scientific instruments were too complicated. The rocket engines weren't producing enough thrust to lift the weight. The deadline was slipping, and Korolev knew something that made every delay feel dangerous. The United States was moving. In July 1955, President Eisenhower had publicly announced that the Americans planned to launch a satellite as part of an international scientific program called the International Geophysical Year, a coordinated global effort to study the Earth from 1957 to 1958. 4 days after that announcement, a senior Soviet physicist named Leonid Sedov held a press conference and announced that the Soviets would also launch a satellite. The race was now official. The clock was running. So Korolev made a decision. He would build something smaller. He would abandon the scientific payload entirely, simplify the design down to its essential function, and launch it before the Americans could. On February 15th, 1957, the Soviet Council of Ministers formally approved this simpler design. The new satellite, designated Object PS, would weigh around 100 kilograms. It would carry no scientific instruments. It would transmit nothing but a pulse, a beep. The entire scientific community initially resisted the idea. What was the point, they asked, of launching a satellite that couldn't measure anything? Korolev's answer, essentially, was, "The point is to be first." But then something unexpected happened. The simplest satellite turned out to be more scientifically useful than anyone had predicted, because the beep itself, that plain, repeating radio pulse, was carrying information. Not the kind encoded in telemetry data, but information that researchers could read from the behavior of the signal as it traveled from orbit to Earth. The density of the upper atmosphere could be calculated by watching how the satellite's orbit decayed over time, how drag was pulling it gradually lower. The behavior of the radio signal as it passed through the ionosphere, the electrically charged upper layer of the atmosphere, revealed data about electron density at different altitudes. The propagation of two separate transmission frequencies allowed researchers to model how radio waves interact with the ionosphere under real conditions. None of this had been the plan. But science, as it so often does, found a way in through the back door. Here is what made the signal more than just a tone. Temperature and pressure aboard the satellite were encoded not in the frequency of the signal, but in its timing. If the temperature inside the sphere rose above 50 degrees Celsius or fell below zero, or if the internal pressure dropped below a threshold indicating a possible puncture, the duration of the beeps would change. The pattern would shift. A receiver on the ground, if you knew how to read it, could tell you whether the satellite was healthy or in trouble. 3 separate switches were built into the system. One for excessive cold, one for excessive heat, one for a loss of pressure, which would have indicated a meteor impact. In the 22 days that the transmitter operated, none of those switches activated. Sputnik was fine, but here's the part that the designers had not fully anticipated, and here is where we plant the seed of what this story is really about. The satellite was talking. It was telling scientists things about the space environment above the atmosphere that no instrument on the ground had ever been able to measure directly. The radio signal that reached the Earth had traveled through the ionosphere. And the ionosphere is not empty. It is full of free electrons and charged ions created by ultraviolet radiation from the sun. These particles interact with radio waves. They absorb some frequencies. They reflect certain wavelengths back to Earth and let others pass through. By studying exactly how the signal arrived at what angle, with what phase shift, researchers could begin to build a precise picture of the ionosphere's structure. The 2 different transmission frequencies behaved differently as they passed through the same region, and comparing them gave additional information that a single frequency alone could never have provided. The ionosphere had been studied from the ground before, but studying it from above, from inside it, from orbit, that was new, and the implications reached far beyond radio communication. Every future satellite, every signal sent from orbit to Earth would have to travel through that region. Understanding how it behaved was foundational, and Sputnik was the first instrument humanity ever had inside it. The launch itself almost didn't happen. The R-7 rocket that carried Sputnik into orbit was not designed for space. It had been built as an intercontinental ballistic missile, the most powerful rocket in the world at the time, developed with excess thrust because the engineers weren't sure how heavy a nuclear warhead might eventually need to be. Several modifications had to be made to adapt it for a satellite payload. A 300 kilogram radio package was removed from the booster. New engine burn times were calculated. A new payload fairing replaced the warhead configuration. The first 3 test launches of the R-7 had all failed. A fire in a booster strap-on, an assembly defect that prevented ignition, an electrical short that sent the rocket into an uncontrolled roll. In the summer of 1957, Korolev wrote to his wife, "Things are very, very bad." The 4th launch, in August 1957, finally succeeded. The rocket flew 6,000 kilometers and deposited its dummy warhead at the intended target. Korolev stayed awake until 3 in the morning, talking to his team about what had just become possible. There were still problems on the night of the actual launch. At 16 seconds after ignition, a fuel regulation system called 1’s failed. The rocket began consuming kerosene at a higher rate than planned. Steering engines had to rotate several degrees beyond their normal range to correct a deviation in the rocket's pitch. The flight control system came within a moment of automatically terminating the mission. And then, the engine recovered. The rocket straightened, and the flight continued. At 295.4 seconds after liftoff, 1 second before the planned engine cutoff, the engines shut down early. Not because of a command, but because a sensor detected that the fuel turbine was spinning too fast, a sign that the fuel had run out. At the moment of cutoff, 375 kilograms of liquid oxygen oxidizer were still aboard. The fuel was gone first. As a result, the satellite entered an orbit that was about 80 to 90 kilometers lower than intended. The intended apogee was around 1,450 kilometers. The actual apogee was 947 kilometers. The perigee, the lowest point of the orbit, was 228 kilometers. This was lower than planned, and that mattered. Lower orbit means more atmospheric drag. More drag means a faster decay. The satellite was going to fall back to Earth sooner than intended. But here is the strange thing. That lower orbit, that miscalculation, that fuel system failure, it was precisely what made the scientific measurements of atmospheric density possible in the first place. Scientists watching the orbit decay over the following weeks could calculate the density of the upper atmosphere by measuring exactly how fast the satellite was losing altitude. The drag was the measurement. The mistake was the instrument. The satellite completed each orbit in 96.2 minutes. It was traveling at a peak speed of roughly 8 kilometers per second. Over its 92 days in orbit, it completed 1,440 trips around the Earth. It traveled a total distance of approximately 70 million kilometers. On January 4, 1958, it re-entered the atmosphere and burned up. The precise location has never been confirmed. A man in Encino, California, reportedly found unusual plastic tubing in his backyard that morning, tubing of the type used in the satellite's construction. No one has ever been able to confirm whether it was real or not. And there is something fitting about that. The first object humans ever placed in orbit, vanishing quietly, without ceremony, in someone's backyard. Or perhaps not. Perhaps it just burned to nothing over the Pacific. We don't know exactly where it went. To understand how strange this moment was, it helps to put it next to what came before and what came immediately after. Before Sputnik, the only artificial objects humanity had placed above the atmosphere were sounding rockets, small rockets that reached the edge of space for a few minutes before falling back. The highest any had reached was several hundred kilometers. None had sustained an orbit. None had transmitted from space for more than seconds. The entire concept of a human-made object circling the Earth continuously, of it being, in any meaningful sense, up there, was theoretical. After Sputnik, it was not theoretical anymore. The United States had been building its own satellite program under the name Project Vanguard. The satellite it planned to launch weighed 1.6 kilograms. Sputnik weighed 83.6 kilograms, more than 50 times as much. The scale of the Soviet achievement was, by any measure, larger than the Americans had anticipated. 2 months after Sputnik, on December 6, 1957, the United States attempted to launch its first satellite. The rocket rose a little over a meter off the launch pad, lost thrust, fell back down, and exploded on the pad in a fireball broadcast live on television. The satellite, barely damaged, rolled off the burning rocket and began transmitting its signal from the ground. A small, helpless beep from the wreckage. The contrast with Sputnik's clean, confident signal from orbit was not lost on anyone. Meanwhile, the Soviets had already launched Sputnik 2 on November 3, 1957, just 1 month after the first launch. This satellite carried a dog named Laika. It weighed more than 500 kilograms. The technology had scaled up dramatically, almost overnight. The United States finally placed a satellite in orbit on January 31, 1958, Explorer 1. It was lighter than Sputnik, but its orbit carried it higher. And in reaching that higher altitude, Explorer 1 made a discovery that Sputnik, with its simpler orbit and simpler instruments, could not have made. it detected the bands of intense radiation encircling the Earth, now known as the Van Allen radiation belts. Sputnik had opened the door. Explorer had walked through it, and what they found together, the ionospheric data, the atmospheric density measurements, the radiation belts, became the foundation of every space program that followed. What's worth pausing on is this. Neither satellite was designed primarily for science. Sputnik was designed to be first. Explorer was designed to catch up. The science was almost incidental, and yet the science was extraordinary. That is a pattern that would repeat itself throughout the entire history of space exploration. The political competition produced the technology produced the knowledge, and the knowledge, in almost every case, was more surprising than anyone had expected. There is a detail about Sputnik that gets overlooked in almost every telling of the story. The satellite was not immediately used for propaganda. The Soviets had a habit, carefully cultivated over years, of keeping quiet about their accomplishments in rocketry. They feared that success would invite scrutiny, and scrutiny might reveal failure. So, the morning after the launch, the official Soviet newspaper Pravda published only a few paragraphs about Sputnik on its inner pages. Not the front page, not a headline, a few paragraphs. Khrushchev, when he was told the satellite had successfully reached orbit, congratulated the engineering team and went to sleep. He had not yet understood what had happened. Within days, the scale of the reaction in the West made everything clear. American newspapers were using the word crisis. Citizens were writing letters to their government. A university poll would later show that more than a quarter of Americans believed Soviet science and engineering had surpassed American science and engineering. The political and psychological shock of the beeping sphere was something the Soviets had not planned for and something the Americans had not braced for. Eisenhower, privately, had known it was coming. The CIA had been monitoring Soviet rocket development for years through intelligence gathered by U-2 spy planes. He had been briefed. He understood the timeline. He was not surprised. But he had deeply underestimated what his own public would feel when they heard the sound from space. The response was transformative. The United States created the Advanced Research Projects Agency, later renamed DARPA, in February 1958, specifically to regain a technological lead. It passed the National Defense Education Act, providing federal funding for science and mathematics education at every level for the first time. It established NASA, and it committed, eventually, to the most ambitious peacetime engineering program in human history, the effort to reach the moon. All of this from a sphere the size of a beach ball. All of this from 22 days of beeping. Now, here is what Sputnik actually found when it reached orbit, and this is the part that takes a moment to sit with. The satellite was launched into a universe that humans had never directly touched. Before Sputnik, everything we knew about space above the atmosphere was inferred, guessed at, modeled from the ground. The ionosphere, the upper atmosphere, the behavior of radio waves at orbital altitude, these were all theoretical. We had never been there. We had never sent anything there that could tell us what it was like. Sputnik went there and reported back, not in words and not in data tables, in the shape of its orbit as it decayed, in the behavior of its signal as it passed through layers of charged particles, in the difference between the two frequencies it transmitted and how they arrived at different angles and phases to receivers thousands of kilometers below. The beep was not just a beep, it was a measurement, the first real measurement ever taken from orbit. And here is what the measurement said. The upper atmosphere is there, it is real. It has density and structure, and it changes over time. The ionosphere is not a simple boundary, but a complex, layered environment that responds to the sun, to its ultraviolet output, to the 11-year cycle of sunspot activity, to the time of year and the time of day. Radio signals don't just pass through it cleanly. They bend and scatter and absorb, Understanding that environment would turn out to be essential for every piece of technology we now take for granted: satellite communications, GPS, weather forecasting, global navigation, and we began to learn all of it from a small metal ball that beeped for 22 days. Two physicists at Johns Hopkins University, William Geer and George Weifenbach, were monitoring Sputnik's radio transmissions within hours of the launch. They realized that the Doppler shift of the signal, the way its apparent frequency changed as the satellite moved toward and then away from them, could be used to calculate exactly where the satellite was along its orbit. Their director gave them access to the university's mainframe computer to pursue the calculations. And within months, they had been asked to solve the inverse problem: not finding the satellite from a known position, but finding the receiver's position from a known satellite. That work became the transit system, the first satellite navigation system, the ancestor of GPS. The signal from a small metal sphere, launched in secret, received by amateur radio operators in their living rooms, tracked by a telescope in rural England, photographed by an observatory in Canada, decoded by two physicists at a university in Baltimore. This signal-seeded technology that would eventually guide every aircraft, every ship, every car, every phone on the surface of the Earth. Korolev once stood over the satellite's polished casing before launch and shouted at a junior worker who had left a smudge on it. "This ball will be exhibited in museums," he said. He was right about that. Replicas and backup units now sit in museums on every continent. The signal is long silent. The sphere itself burned up over the atmosphere on a January morning in 1958, somewhere above the western United States, or perhaps not there at all. We don't know exactly. But the effects of that 2-day conversation between orbit and Earth have never stopped radiating outward. The Soviet Union launched a satellite to win a political competition. What they found when it reached orbit was something no one had planned for: a universe that was willing to be measured. An atmosphere that had been waiting to reveal itself to the right instrument. A silence above the clouds that turned out to be full of information if you knew how to listen. The engineers in that room in Kazakhstan listened, and what they heard that night, steady, rhythmic, impossibly clear, was not just a proof of concept or a Cold War victory or a technical milestone. It was the first time the Earth had ever heard its own reflection from space. We built the machine. We launched the rocket. We listened for the signal. And for 22 days, the sky answered, beeping quietly through the dark, once every 96 minutes, over every continent, over every ocean, seen by anyone who looked up at the right time and knew what they were looking for. We have been listening ever since. There is something deeply strange about what happened in the weeks after Sputnik reached orbit. The Soviet Union had just accomplished something no nation in human history had ever done. They had placed an object in orbit around the Earth. They had beaten the United States to space. They had announced the achievement to the world through TASS, the official state news agency. And yet the men who had actually done it, the engineers and scientists who had spent years of their lives building the rocket and the satellite, were immediately made to disappear. Not literally, but from history. Sergei Korolev, who had lobbied for the satellite for years, who had designed the rocket program that made it possible, who had stood in the launch bunker on the night of October 4th, watching the engines ignite, his name was removed from the public record. New editions of histories that had previously mentioned him were reprinted without his name. Soviet encyclopedias listed him only as a laboratory head at an unspecified machine-building institute. He published articles in Pravda under the pseudonym Professor K. Sergeyev. Mikhail Tikhonravov, the engineer who had been writing theoretical papers on orbital satellites since the late 1940s, who had co-authored the original technical report that gave Korolev the scientific grounding to approach the government, who had been with the project from its very first meeting. He did not even have a pseudonym. He simply ceased to exist in the official record. Valentin Glushko, who had designed the rocket engines. Mstislav Keldysh, the mathematician and Academy of Sciences vice president who had chaired the scientific commission overseeing the satellite's development. Both were referred to in the press only by their titles: Chief Designer of Rocket Engines, Chief Theoretician of Cosmonautics, stripped of the names that would have made them human. Khrushchev explained this publicly at the time. He said their identities were being concealed for the security of the state. And that was partly true, but it was also something else. The Soviet system had a complicated relationship with individual achievement. The triumph of Sputnik was to be a triumph of the Soviet people, of the Soviet system, of socialism as a method of organizing human effort. It was not supposed to be the triumph of a man. Korolev seems to have accepted this, or at least to have lived with it. He was allowed to write in Pravda under his pseudonym. His real work continued. His real authority within the program was unchanged, but the world did not know his name. In the United States, the reaction was the opposite. The names of American scientists and engineers became celebrated in the press, testified before Congress, held up as symbols of national capability. Wernher von Braun, the German rocket engineer who had been brought to the United States after the war and who would eventually help build the rockets that reached the moon, was a public figure, photographed, interviewed, known. In the Soviet Union, the chief designer remained a ghost. And yet it was the ghost who had done it first. On October 9th, 1957, 5 days after the launch, Pravda published a long, anonymous report detailing the construction and design of the satellite. It had been written by Korolev and other members of the design team. Their names did not appear on it, but the work was theirs. Every calculation, every engineering decision, every compromise made under pressure, all of it described in careful technical language, attributed to no one. It is one of the stranger documents in the history of science. A detailed account of a historic achievement written by the people who achieved it, with no names attached. The satellite beeped on through all of this, indifferent to the politics below. Let's go back to the signal for a moment. Because the way the world received it tells you something important about what Sputnik actually was. Not as a political event, not as a scientific instrument, but as an experience. The two transmission frequencies had been announced publicly before the launch in a Soviet radio journal. Amateur operators around the world had been told what frequencies to monitor. This was intentional. The designers had calculated the power requirements specifically so that average citizens, not just professionals with sophisticated receivers, could tune in. The 20.005 MHz frequency was chosen in part because it sat just 5 kHz above a well-known American time standard broadcast. Any shortwave radio tuned to that region of the spectrum would produce an audible beat tone when Sputnik passed overhead. On the evening of October 4th, teams of visual observers at 150 stations across the United States had been alerted to watch for the satellite at dawn, and during evening twilight, radio operators were asked to record its signal. The British tracked the rocket's booster stage using the Lovell telescope at Jodrell Bank Observatory in England, the only telescope in the world at the time capable of doing so by radar. Canada's Newbrook Observatory became the first facility in North America to photograph Sputnik 1, and in living rooms and kitchens across the United States, ordinary people sat next to their shortwave radios and listened. The first recording made outside the Soviet Union was captured by RCA engineers near Riverhead, Long Island. They drove the tape into Manhattan and it was broadcast on NBC radio that night. Meanwhile, students working at Columbia University's ham radio station picked up the signal independently and rebroadcast it over the university's FM station, the first time an American public audience heard the sound of something in orbit. Newspapers described it the next morning in language that oscillated between wonder and fear. Both thrilled and terrified was how one observer described the reaction. A steady beeping tone from 228 kilometers above the ground, passing over at 8 kilometers per second, completing a full orbit every 96 minutes. It was the same sky people had always looked at, and it was now entirely different. What most people actually saw when they went outside to look, though, was not the satellite. The satellite itself was a small, polished sphere just 58 centimeters across, barely visible to the naked eye, even in ideal conditions. What observers tracked crossing the pre-dawn and evening sky was the R7 core stage, the spent rocket booster, 26 meters long and massive enough to qualify as a first-magnitude object visible without any optical aid. The Soviets had placed deployable reflective panels on the booster specifically to make it easier to track visually. So the thing people pointed at, the thing they photographed, the bright object that crossed the sky and made them feel that the world had changed, was mostly the discarded rocket casing. The actual satellite was the barely visible speck trailing behind it. The most visible part of the achievement was the machinery that had made it possible. The actual thing, the small, quiet object doing the work, required more careful attention to find. In Britain, the initial reaction in the press was described as a mixture of fear and amazement, with many newspapers declaring the arrival of the space age. That framing lasted about a month. When the Soviet Union launched Sputnik 2 on November 3rd, carrying a live dog, the tone shifted. Public sentiment in Britain turned sharply against the Soviet program, with protests sent to the Soviet embassy and to the Royal Society for the Prevention of Cruelty to Animals. The scientific achievement and the political system that had produced it were inseparable in the minds of many observers, and the political system was not admired. In the United States, a poll conducted at the University of Michigan shortly after the launch found that 26% of Americans believed Soviet science and engineering had surpassed American capability. A year later, after the United States had begun launching its own satellites, that figure had dropped to 10%. Public perception of scientific national power, it turned out, moved quickly in response to visible demonstrations. The sky was now a scoreboard. The launch of Sputnik did not just start a race, it built institutions. Some of those institutions are still running today. The United States created the Advanced Research Projects Agency (ARPA) in February 1958, 2 months after Sputnik. Its mandate was to ensure that American technology would never again be caught flat-footed by a rival's advance. That agency, later renamed DARPA, funded research that eventually produced the Internet. It still operates today, working on technology that won't be publicly understood for decades. In July 1958, the National Aeronautics and Space Act created NASA. The agency was built directly on the organizational framework and personnel of the National Advisory Committee for Aeronautics, but its mandate was transformed from studying atmospheric flight to reaching beyond it. Within 11 years of Sputnik's launch, NASA would land 2 men on the moon. The National Defense Education Act, passed in 1958, provided federal funding for science, mathematics, and engineering education at every level for the first time in American history. Low-interest loans for college students majoring in technical fields. New curricula in public schools. Investment in science laboratories and teacher training. The educational infrastructure of the American technological workforce was restructured in significant part as a direct response to a beeping sphere. Harrison Storms, the aerospace engineer responsible for the X-15 rocket plane and later for key elements of the Apollo command module and Saturn V's second stage, later said that the launch of Sputnik was what made him think of space as the next step for America. Alan Shepard, who in 1961 became the first American in space, said that seeing Sputnik pass overhead was among the experiences that shaped his decision to become an astronaut. Deke Slayton said the same. A sphere the size of a beach ball, beeping for 22 days, inspired a generation of engineers and scientists who would spend the following decades building the infrastructure of space exploration. It also, more quietly, planted the seed of satellite navigation. 2 physicists at Johns Hopkins University's Applied Physics Laboratory, William Geer and George Weifenbach, were monitoring Sputnik's transmissions within hours of the launch. They were not tasked with this. They did it because they were curious. And within a short time, they realized that the Doppler shift of the satellite's signal, the change in apparent frequency as the satellite moved toward and then away from their receiver, allowed them to calculate the satellite's precise position along its orbit. Their laboratory director gave them access to a UNIVAC computer to work through the calculations. And early the following year, the deputy director of the laboratory asked them to turn the problem around. If you can find the satellite from a known position, can you find the position from a known satellite? The Navy was developing a submarine-launched missile at the time. Submarines needed to know their precise location to fire accurately. The answer to Gear and Weifenbach's inverted problem led directly to a satellite navigation system called Transit, the direct ancestor of the global positioning system that now guides every aircraft, every ship, every emergency vehicle, and every phone on the planet. None of this was planned. None of this was in the original mission parameters for a simple satellite carrying no scientific instruments. It emerged from curiosity, from the impulse to listen to an unexpected signal, from two physicists staying late in a laboratory because something new was passing overhead and they wanted to understand it. That is, when you trace it all back, exactly what science is. And the Russian word for what Korolev had built, Sputnik, means literally traveling companion or fellow traveler. The satellite was, in that sense, precisely what its name described. It traveled with us. It accompanied a generation through one of the most consequential transitions in human history, from a civilization confined to the surface of one planet to one that had reached beyond it. Even the word entered the language. The American writer Herb Kahn, writing in the San Francisco Chronicle in April 1958, coined the term beatnik, attaching the Russian suffix to describe a generation of young Americans who seemed to be orbiting outside mainstream culture. The suffix "nik" spread through English slang and stuck. Sputnik changed not just aerospace, but vocabulary. On October 26, 1957, 22 days after launch, Moscow radio announced that the satellite had gone silent. The 3 silver-zinc batteries had depleted. The transmitter stopped, the beeping ended. The sky, to anyone tuned to 20.005 MHz, was quiet again. The sphere was still up there. It was still orbiting, still following its elliptical path between 228 and 947 kilometers above the surface, still tilted 65 degrees to the equator, still completing a full orbit every 96 minutes, but it was no longer talking. Over the following weeks, ground stations continued to track its position optically and by radar. The orbit was slowly decaying. Atmospheric drag, working on even the thin wisps of air at orbital altitude, was pulling the satellite incrementally lower with each pass. Researchers were using this decay, measuring it precisely to calculate the density of the upper atmosphere at different altitudes. This was not a coincidence. This was the measurement Korolev and his team had built into the design, even without scientific instruments aboard. The sphere itself, through the geometry of its decaying orbit, was the instrument. The R-7 core stage, the spent booster rocket that had also reached orbit and had been visible to observers as the brighter of the 2 objects crossing the sky, re-entered the atmosphere on December 2nd, 1957. It had completed 882 orbits. It burned up somewhere over the Earth, leaving no trace. The satellite itself lasted longer. Smaller, lighter, producing less drag, it clung to its orbit through December and into the new year. On January 4th, 1958, after 1,440 orbits and approximately 70 million kilometers of travel, it re-entered the atmosphere. Somewhere over the western United States, most likely. Though the exact location has never been confirmed, it burned up. 3 months after launch, the first satellite in history was gone. What remained was everything it had set in motion. In the months and years that followed, the Soviet Union launched Sputnik 2, carrying the dog Laika, making her the first living creature to travel in space, and then Sputnik 3, which was the original Object D that had been pushed aside to make room for the simpler satellite. Sputnik 3 weighed over 1,000 kilograms and carried 12 scientific instruments. Its data confirmed the existence of two radiation belts encircling the Earth, the inner belt composed primarily of protons, the outer belt composed largely of electrons. These belts, already detected in part by America's Explorer 1 satellite, would come to be known as the Van Allen belts. The picture of Earth's space environment, begun with a beeping tone from a polished sphere, was filling in rapidly. The CIA, it later emerged, had been monitoring Soviet rocket development for years and had briefed President Eisenhower before the launch. Declassified documents released decades later, 59 documents and 440 pages, revealed the intelligence picture the CIA had assembled of the Soviet space and missile programs from 1955 onward. The American government had not been surprised. The American public had. That gap between what governments knew and what citizens felt defined the political experience of Sputnik more than any technical detail. Eisenhower had tried to publicly downplay the significance of the launch, calling it no great surprise. His advisors privately worried that this calm tone was making things worse. The public did not want calm. They wanted a response. They got one. Funding poured into universities, laboratories, and aerospace companies. The military and the scientific community began communicating in ways they never had before. Political campaigners exploited fears of a growing technological gap between American and Soviet capabilities, what became known as the missile gap, for years afterward. That fear helped carry John F. Kennedy to the presidency in 1960, running on a platform of renewed national ambition in science and defense. And Kennedy, in 1961, announced the goal of reaching the moon before the decade was out. The chain is unbroken. A fuel system failure on a converted missile. A satellite placed 80 kilometers lower than intended. A 2-2-day transmission. And then GPS. NASA, the Internet's ancestor, federal science education funding, Apollo, and the modern conception of space as a place humanity belongs. All of it traceable, in a direct and documented line, to a small metal sphere that beeped through the night of October 4th, 1957, above the heads of everyone on Earth. Most of them didn't know it yet. Some of them looked up and saw the rocket booster cross the sky and thought they were seeing the satellite. They were pointing at the wrong thing, but the impulse to look up, to track a moving light, to feel that something had changed that impulse was right. Something had changed. The question of what kind of creatures we are, whether we are a species confined to one planet or one capable of reaching beyond it, had just received its first tentative answer. Sputnik did not answer it completely. No single object could, but it asked the question out loud, in a language everyone could receive, on a frequency anyone with a shortwave radio could tune to, and 68 years later, we are still working out what the answer means.